this is number 88. I'm going to do part B. It's asking us to calculate the empirical formula for, in this case, vanillin, which is actually what gives that taste and smell of vanilla. And so we're going to determine the empirical formula. The empirical formula is that simplest representation of the ratios of one element to another in a molecule. And we're given some information. We're told that by mass we have 63.15% carbon in vanillin. We have 5.30% hydrogen in vanillin, and we have 31.55% oxygen in vanillin. These are all mass percents. So the first thing to make things easy with this type of question is just assume 100 grams of sample. Assume that we have 100 grams of vanillin that gave us this result, the 63% carbon, 5% hydrogen, 31% oxygen. We assume 100 grams because then that allows us to say, well, we have really 63.15 grams of carbon. We really have 5.30 grams of hydrogen. And we have 31.55 grams of oxygen. Again, since these are percents, right, the molecule only contains carbon, hydrogen, and oxygen, so those percents should add up to 100%. And so if we assume 100 grams of sample, then those percentages actually just turn into an actual mass. So 63.15% in a 100 gram sample is 63.15 grams, and so on. So to get the empirical formula, we have to determine moles, right? That's the first thing we need to do. So we first assumed 100 grams, but then we're going to use our atomic masses to convert out of grams and into moles. And so we look on the periodic table. Carbon weighs 12.01 grams per mole, and so that gives us 5.285 moles of carbon. We're going to do this for each one of our elements. The atomic mass for hydrogen is 1.008, and that gives us also 5.258 moles of hydrogen. Sorry, I got these two numbers backwards here. This should be 258. So same moles of carbon to the same moles of hydrogen when you do that calculation. And then when we use oxygen, oxygen weighs 16 grams per mole, and we get a value of 1.972 moles of oxygen. So while we can't relate mass of one element to mass of another, we can relate moles of one element to moles of another. Right? With masses, all these elements have different atomic masses, and so that's why we can't relate one mass to another mass. But once we are in terms of moles, now these mole values are really the ratio for the empirical formula of vanillin. And so I'm just going to erase this on the left here and take these numbers and write them a little bit differently. So we know that we have this molecule that contains carbon, hydrogen, and oxygen, and now we know their mole amounts, 5.258, same with hydrogen, same with oxygen with its value being 1.972. So I just took those mole values that we calculated and put them as subscripts for the ratio of carbon to hydrogen to oxygen. Now, we can't have a fraction or a decimal in this formula, right? Remember, formulas have to be whole numbers. So to make things simple, what we'll do is we will divide by the smallest value to hopefully simplify the ratios. And when we do that, we get C to be equal to now that ratio 2.66. We get hydrogen to also be 2.66, and then oxygen would just be 1. So we took the mole values that we calculated for carbon, hydrogen, and oxygen, and then we put them into where the whole number unit would go for the ratio of carbon to hydrogen to oxygen. Once we did that, we divided by the smallest value so that it would go to 1, and we were hoping that the other ones would simplify as well, but unfortunately they did not. So we need to do one step further. And so we have to realize that the fraction that corresponds to 0.66 is 2/3. So that means if I multiply through by 3, I can get rid of my fraction and reach a whole number. And so if we take 2.66 times 3, we actually get a value of 8. And so if we do that, we're multiplying through each one of these guys by 3, we get C8, H8, O3. And that is the empirical formula for vanillin. So we had to use the mass percents to get into mass of each element. From the mass of each element, we got the moles of each element. That allows us to set up this ratio of one element to another. We then simplified the ratio by dividing by the smallest mole value. We realized that that didn't help us out. It helped us out a little bit with the oxygen, but we still have fractions with the carbon and hydrogen. And then realizing what that actually means in terms of a fraction, we can actually simplify by multiplying through each element by 3 so that the fraction drops out and leaves us then with the simplest representation for this molecule, the empirical formula, which is C8H8O3.